because, I mean, the course is changing pretty dramatically, like, for next year, so it's not like we're going to be reusing any of those tests again. So I'll try and get you some or most of your old tests back today. We're working on some problems later on, and then certainly whatever I don't get back today, I'll get back hopefully on Friday. So our remaining objectives from topic 9.4 are to state that gravitation provides the centripetal force for circular orbital motion. We have a number of derivations today. We need to derive Kepler's third law. We also need to derive expressions for the kinetic energy, potential energy, and total energy of a satellite that's orbiting something. We want to sketch a graph to show how those energies vary with distance from the planet or distance from the thing that we're orbiting. We want to discuss the concept of weightlessness in a few different contexts, and then solve problems involving orbital motion. All right. So when we talk about satellites, it is a very healthy model to think of like artificial satellites or communication satellites. But what else is a satellite? Yeah, moons are satellites, right, of whatever planet they orbit. What else?
Asteroids.
Asteroid is a satellite of the sun. Planets are satellites of stars and of the sun. Yeah, so really anything, even the sun, or our solar system would be a satellite of the galaxy. Probably might not make sense to call the galaxy a satellite of the universe, but yeah, anything that orbits something else is what we mean by a satellite. So here, right, we have this huge cannon, and if we fired something fairly fast, not nearly as fast as the escape speed, right, because we're firing horizontally. But if we fired something fairly fast, right, gravity brings it down. But if we fire it fast enough, right, gravity continues to act, but that inward force would really just serve to provide circular motion, right? If the speed is fast enough that the Earth curves out from underneath our projectile, then we can have a satellite. All right, so that's the kind of thing that we are addressing today. So here is a diagram that shows a number of different attempts to launch a satellite into orbit, and it looks like all of those attempts are successful. So we have the cannon actually facing to the left. With a relatively small speed, we've put that satellite into orbit, right? And if we go faster and faster and faster, we kind of go from, I think this one is the circular orbit, but we go from a circular orbit to a more and more and more elliptical, more and more eccentric orbit. And probably, we could launch it, not probably, we could launch it fast enough that it actually wouldn't. Call that a satellite? I don't know. Launch it fast enough that it actually kind of gets over by somebody else and maybe becomes a satellite to them. Maybe we start getting too complicated. But if we launch a satellite in this way, it would be the launch speed that would kind of determine the shape of the orbit. Now, orbital motion of these satellites could be circular, it could be elliptical, it could be parabolic, but IB specifies that for this topic we really only need to care about circular orbits, which means that we get to revisit some of our centripetal forces and our circular motion objectives. And our first objective for today was merely to state that gravitation is providing the centripetal force that keeps a satellite in circular motion. All right, so follow-up questions from anybody about gravity being the agent of the centripetal force for satellites. Great, so that's our first objective, 5 more to go. Last year, we did discuss all 3 of Kepler's laws. To refresh your memories, the first law was the one that said that the planets follow elliptical paths, and the sun is at one focal point. What's at the other focal point? So the Earth goes around the sun, right? It's not a perfectly circular orbit. It's pretty circular, but not perfectly circular. The sun, so let's see, so here's the Earth, right? Here's the sun. What's here? What? Yeah, probably nothing. Probably just empty space. Great. So Kepler's first law says the sun is at one focal point, but there's not necessarily anything at the other focal point. Remember how we just said that we come up with these eccentric orbits. right? I mean, if we do put this satellite here into an eccentric orbit, the center of the Earth is here, that would be one of the focal points. Then there doesn't need to be anything at the other focal point, right? I mean, this orbit's small enough that we have center of the Earth here and off-center from the Earth here, but if we fired it faster, like for this one, then the other focal point's probably down here somewhere. All right, so the first law told us about the shapes of the planet's orbits. The second law was the one about the planets sweep out equal areas at equal times, and that's why we go faster when we're closer to the sun and slower when we're further away. And then the third law was the equation one. Do I want to get that up here? I do, but I'm going to cheat. All right, so Kepler's third law, as we had it last year, was TA over TB squared. And what did the T stand for? The period of the planet, right? Well, planet A and planet B. And then RA and RB cubed, where R is the orbital radius of the two planets. All right, so Kepler's third law was that equation, and I don't recall deriving it for you. It is within the realm of possibility that I did, but I don't recall doing it. I've lost my erase. Usually behind my computer or something, and I can't find something like that.
It's over there.
Probably over here.
What do you use for the radius of a elliptical orbit?
So what do we use? If it's a circular orbit, it doesn't really matter too much. If it's non-circular,
Average.
well, yeah, but then what does average mean? I'm not sure. All right, so we need to derive this. Our starting place, like most of the derivations we've done, either start with mechanical energy or with Newton's second law, and this one is we start with Newton's second law. All right, so Newton's second law tells us that the net force acting on something is the mass times the acceleration. And what is the only force acting on a planet? Gravitational pull from the sun. All right, so the gravitation is equal to, right, the net force, which is mass times acceleration. Okay, so that's our starting point. And then we need to end up, we're not going to end up with this exactly. What we are going to end up with, though, is really TA over R at TA squared over RA cubed equals TB squared over RB cubed. We're going to end up with something that looks more like that. So it's not difficult so long as we know the starting place. All right, law of universal gravitation is our Gm over R squared. And then this is a centripetal acceleration. And one of our expressions for centripetal acceleration is 4 pi squared r over t squared. Right? That comes from v squared over r, and v equals 2 pi r over t, the circumference divided by the period. Right? So if we just merge that into here, we get 4 pi squared r over t squared. Okay, we can obviously cancel out the smaller n. And then, what can we do any other canceling out? Can I cancel out any r's with each other? I don't think so. No, I don't think I can. So let me just rewrite this without the small m's, and then we'll see what we can do. Alright, I really can't do anything. I can't cancel out anything else, but what I would like to do is move all my r's and t's to one side, and everything else to the other side. So the gm I'm going to leave here, but I'm going to bring the 4 pi squared over to the left as well. And then I'm going to move the r squared over to the right. Alright, and I'm left with something that actually looks uglier than when we started, but we're actually done. Big G is a constant, that's the universal gravitation constant. If we're talking about planets, whose mass is this? Whose mass is the bigger one? The sun. Okay? This was the gravitational force acting on the planet is the planet's mass times its centripetal acceleration. So we have the mass of the sun, and then 4 pi squared, obviously, are constants as well. So everything I have on the left-hand side is a constant, so long as we're only talking about planets. And that must mean that the ratio of r cubed to t squared is a constant as well. So for any planet in the solar system, its orbital radius squared divided by its period squared is the same as for any other planet. And that's Kepler's third law, where it's the orbital periods of the planets to their orbital radii. Alright, so really all we did was use Newton's second law, replace the net force with the gravitational force, replace the acceleration with centripetal acceleration, and canceled out the mass of the planet in both cases, and we get Kepler's third law. Robbie?
I might be going crazy. When you multiply 2 pi r over t and you squared that, why wasn't r squared?
Why isn't r squared?
Yeah.
Because we have an r.
Oh.
Right?
It cancels out, okay.
Other issues with deriving Kepler's third law. Okay, onward. Now we get to derive some more expressions for our energy of orbiting objects, or energy of satellites, right? So let's do kinetic energy first. So kinetic energy, we hopefully remember from, a class ago, is 1/2 mv squared. But we don't want that. We want a different expression for kinetic energy. So my starting place here is also forces, and if we do have a satellite or a planet or whatever orbiting something, right, again, the gravitational force is acting as the centripetal force. So my starting place for this one is very similar to my starting place for the other. Alright, centripetal force is mass times centripetal acceleration. Gravitational force is gmm over r squared. And this time, what do I want to do? I want to put in the v squared. I need this to look like kinetic energy. And it doesn't look that much like kinetic energy right now. So I'm going to put in m v squared over r, right, instead of centripetal acceleration. I'm going to leave the right-hand side alone. And this looks a little bit like kinetic energy now, but kinetic energy has no r in it, so let me get the heck rid of the r. So if I multiply both sides by r, then this r cancels out the square. And that almost looks like kinetic energy. What do I still need to do? I need to divide it by 2. Right? Kinetic energy is 1/2 mv squared. This is mv squared. So I need to divide it by 2, or multiply it by 1/2. And I got to divide the other side by 2 also. Alright? So the typical way of talking about the kinetic energy of an orbiting object is to say gmm over r. Right? That way we don't actually have to know the speed. If we know the mass of it, if we know the mass of the thing it's orbiting, if we know how far away it's orbiting, then that's our kinetic energy. Oh, I messed up. Oh my gosh, sorry. I forgot to carry the 2 over. Alright, questions on arriving at, and is that in your data booklet? Let's look and see. I know Kepler's third law is not there. No, it's not. No, it's not. But it's not going to be as bad. You might be able to not derive it for some uses. All right, potential energy of an orbiting satellite is the same as our gravitational potential energy equation. There's no special version. And gravitational potential energy was negative gmm over r. Right? We derived that maybe 4 lessons ago. I'm happy to derive it again for you, but we've already done that a couple of times in our notes. All right, that came from, where did that come from? That came from our definition of potential energy, which is the work done in moving a small mass from infinity to its location in the field. Right? And work is force times displacement. Okay? So if work is equivalent to the potential energy, force is our gravitational force, And then displacement actually is the same thing as the distance from the source of the field. Right? And then we just shove a negative sign in front, since we said all potential energies are negative. All right, so we already have an expression for the potential energy of an orbiting satellite. And the other one that we need to derive is an expression for the total mechanical energy of an orbiting satellite, which would be the combination of the potential energy and the kinetic energy. Right, so that's fine, but we can do one step better by just putting in our two expressions for the individual mechanical energies. And then we can combine these together, right? If we give both a denominator of 2r, if we do like a common denominator there, we can simplify this to be negative gmn over 2r. So, for kinetic energy, yes, you have to be able to derive it, but we're helped out a little bit because the kinetic energy is exactly half of the potential energy, but positive. Right? So either we need to be able to derive it, or we need to remember it's half the potential energy. Alright, and yet none of those are in the data booklet, so anytime that you're asked to solve for the energy of a satellite, you've got to go through at least pieces of this to be able to do that. Alright, I'm going to move on. This is being recorded, it'll be posted in case you need to see that slow down a little bit. Our next objective is to look at the variation in these three energies as a function of distance from whatever the heck we might be orbiting. So some things to keep in mind to help us do that is that we've been saying for about 4 classes now that potential energy of an object is 0 when we're infinitely far away, and it's negative everywhere else. So here's what these graphs look like. So we have energy on the y-axis, and we have distance from the center of whatever the heck we're orbiting on the x-axis, which is, and 0 energy is here. So our x-axis is here. So which is the pink one? Well, the pink one starts off very, very, very negative, and then works its way closer to the x-axis. That is our potential energy, which is the only one that should be positive ever. Kinetic energy, right? And any place we look, the kinetic energy should be half of the potential energy, right? Here the potential energy is 1 box down, the kinetic energy is half a box up. Here the potential energy is 2 boxes down, the kinetic energy is 1 box up, right? And then the total energy should mirror the kinetic energy, but be negative, or again, wherever the potential energy is, the total energy is half, or half the way to 0, right? Potential energy is half a box, total energy is a quarter of a box. All right, so we are asked to be able to sketch how the variation with these things with distance from whatever it's orbiting. All right, let me slow down and ask for questions at this point, and then we actually only have one objective left before we get to the opportunity to use these expressions a little bit. Okay. Our last objective involved the concept of weightlessness. And in particular, we wanted to discuss that concept for these 3 different scenarios, 3 different contexts. So weightlessness, to me, means that gravitational force equals 0. Right? Gmn over r squared equals 0. However, some people say if you stand on a scale and the scale shows no weight, you're weightless. So if we are in free fall, that means that we are like falling just under the influence of gravity. So the free fall means no air resistance, right? We're just falling under the influence of gravity. Do we have a weight of 0? I don't think so. In fact, if we're close to the Earth, we're falling so that our acceleration is 9.81 meters per second squared. If our acceleration is 9.81 meters per second squared, we certainly have a weight, right? That force is making us accelerate. So we definitely don't have, we do have weight if we're in free fall. But if we stood on a scale, it wouldn't say anything because the scale is falling, we're falling, we would not be compressing the springs of that scale. So there would be an apparent weightlessness. Like last year when we did the problems with like the scale force, right? We were accelerating and on the elevator. We would have an apparent weight that was different from our true weight. And if we were falling at 9.81, the scale would read 9. Alright, so free fall, we don't have a true weightlessness, but maybe we can say we have an apparent weightlessness. If we are a satellite orbiting a planet, is the weight equal to 0? Alright, your foursomes talk about it. We need to be able to confidently answer that question. If you're a satellite, is your weight equal to 0?
No, there's a force. No. It's just not going to do it.
Okay. Is our weight 0, yes or no?
No.
Absolutely, positively not. Right? If our weight was 0, we wouldn't be a satellite. If this wasn't pulling on us, we wouldn't orbit. We would continue in our state of motion until somebody else pulled on us. So absolutely we have a weight. It's a little bit less, maybe even a lot less than if we're at the surface of the planet, but we definitely have a weight. That's the agent of that centrifugal force. But again, there would be an apparent weightlessness. If we were standing on a scale, the scale would read 0 because we are both falling together. We are both accelerating together. Alright, so the astronauts on the space station look like they're weightless because there is, because the shuttle and themselves are falling around the Earth together. Okay, deep space, what's that mean? What does that mean? What?
A location in space where there's no objects pulling.
Deep space means we're way far away from anything. Right? Way far away from planets, way far away from stars, whatever. In deep space, is our weight equal to 0? Well, then we're getting close. Right? Then we're getting close. Because if the R is pretty big, the denominator is pretty big, then this approaches 0. It's still not 0, but it approaches 0. So that's at least the closest to being weightless that we would be. Robbie, then Elizabeth. Yep.
Do they consider deep space like the area in between like Earth and Mars?
No, definitely not.
No,
definitely not, because if we shove something in between Earth and Mars, it's going to orbit the sun. No.
Oh.
If it had some tangential velocity.
Oh, right.
So it's pulling on it quite hard. Elizabeth?
If there's an object between like 2 planets,
Yes.
and it reached the spot between the 2 planets, that was
So no net force. Alright. So here's the Earth, and here's the Moon, and we went to the perfect place, which would be about here, where the force from the Earth and the force from the Moon would be opposite directions. Would I call that weightless? I don't think it's any more weightless than, well, so would there be an apparent weightlessness? I think there would be an apparent weightlessness. I think if I stood on a scale, I don't think the scale would read anything, but I definitely have a weight. They're pulling on me. So yeah, I would say I have an apparent weightlessness, but I do have a weight. However, that is not one of the contexts that IB said we should be able to discuss. But that's interesting. I hadn't thought about that spot in terms of weightlessness.
What if we do like
Daniel? Yes. Well, so have we ever reached deep space? We've actually, I think just in the last 2 years, we have launched something out of the solar system. Is that true?
Well, I know we're going
I
past
know we
like,
launched stuff past Pluto.
the Kepler.
I don't think we've launched anything out of the Kuiper belt or the Oort cloud.
I think they're approaching the zero.
Yeah, I mean, I think we've gotten close. We've either reached or gotten close to like the edge of the solar system, and the solar system would be defined as the area in which things are gravitationally bound to the sun. So once we get past that, that means at least the gravity from the sun is no longer the dominant thing controlling the motion. So have we ever launched something to deep space? Maybe. Maybe. I would consider out of the solar system to maybe qualify as deep space. Yeah.
Just expanding on that, is there an area in between, like, is the next star to the sun, the next closest star to the sun, close enough where as soon as you leave, like, like if you use escape
So
speed
is
to
there
get
anything is there anything in between our solar system and the next one, or does it go right from one to the other?
Yeah,
I think there's definitely a lot in between. And there's definitely a lot in between.
but that would be considered deep space.
I mean, or should it be reserved for the area between galaxies? It's kind of, I don't think there's a concrete answer.
Is there anything between galaxies?
Is there anything between galaxies? Potentially.
Is the stuff in between galaxies the same stuff that's in between, like, planets, just like a vacuum?
In between planets? I don't think so. Alright, so I do have 4 questions, and only 4 questions, on these objectives that I'd like you to work on in your foursomes. I do want to work on distributing old tests, like while you're working on these. So I'm going to post the CD file answers, but I'd really rather you try and get help from other foursomes, since I want to get stuff back to you, and then I can come help, once I've done a few tests back to you. All right? So I'll put the answers from the CD file up on the board, and then maybe, I don't know, maybe we're done in 20 minutes, maybe we're not done until the end of the period. But it would be great if we could do some other stuff in that time.